Today we will discuss about the idea of linear combination of vectors in a vector space. Though this concept is not new for most of us, it's good to recall the idea in the context of linear algebra. The understanding of linear combination of vectors, followed by the idea of spanning set and linear independence of vectors, helps us to move towards the key concept of linear algebra, such as dimension and basis of a vector space. In this video, I am going to discuss about the definition of linear combination of vectors in a vector space and a statement of a theorem which talks about the relationship between the subspaces of a vector space and the linear combination of vectors in the vector space. Also, some examples to show how to express a given vector as a linear combination of a set of vectors in a vector space, taking the vectors as n-tuples, polynomials, as well as matrices. Finally, we are going to see how to relate the idea of linear combination of vector with the idea of solving system of linear equations. First, we will discuss about the definition of linear combination of vectors. The definition of linear combination of a vector: let V be a vector space. Let S be a non-empty set in V. It contains the vectors V1, V2, V3, Vr. Let W be another vector in V which is not a member of S. If W vector can be expressed in the form K1 V1 vector plus K2 V2 vector plus etc. Kr Vr vector, then W vector is said to be a linear combination of vectors V1, V2, etc. Vr in V. Here, the coefficient constants K1, K2, Kr are scalars and are sometimes referred as the weights or coefficients of the linear combination. So, if you are able to express any element of a vector space as a linear combination of set of vectors in S, then the arrangement of the vectors will be in the form of K1 V1 vector plus K2 V2 vector plus Kr Vr vector. We are checking whether an appropriate weights are added to the set of vectors in S to produce the element in V. Let us see the statement of the theorem which relates the idea of subspaces with a linear combination. If S is a non-empty set of vectors in a vector space V, then the set W of all possible linear combination of vectors in S is a subspace of V. Further, that subspace is the smallest subspace of V that contains all the vectors in S. Let us understand this statement of the theorem with a simple example. Here, the larger circle represents the vector space V. This inner circle represents the subspace of a vector space, and innermost circle represents the set S, which contains finite number of elements of V. Let us assume the vector space as R5, 5-dimensional real vector space. Let us choose the vectors 1 0 0 0 0, 0 1 0 0 0 and 0 0 1 0 0 as 3 vectors in R5 space. Those 3 vectors are collected in a set called as S. Now we got a set of non-empty vectors in R5. Now we are going to explore about the first statement. What happens if we make all possible linear combination of vectors in S? That produces the vectors in R3. That means any vector in R3 can be expressed as a linear combination of vectors in S. You can easily understand this because these three elements are nothing but the elements similar to I cap, j cap, k cap in R3. So all the vectors in R3 can be expressed as a linear combination of vectors in S. Now R3 is a subspace of R5. Further, R3 itself is a vector space. So if we chosen a set of vectors in V, and if we collect all possible linear combination of those vectors in V, it is a subspace. So V1, V2, V3 generates all possible vectors in R3, which is a subspace of R5. Further, if we choose any subspace containing S, for example, if we are choosing R4 vector space as a subspace of R5, which contains these three elements in S, then this R4 subspace contains the subspace R3, which is generated by the set S. That is the meaning of the second statement. So the set R3 is the smallest subspace of R5 that contains all the vectors in S, in the sense that any other subspace R4, for example, that contains those vectors contains W. So R5 is a vector space. If we pick set of three elements in S, that generates R3 space, which itself is a vector space and subspace to R5. If I pick one more subspace R4, which is contained inside R5, definitely that R4 encloses R3. So R3 is the smallest subspace that contains all the vectors in S, in the sense that any other subspace that contains those vectors contain W. To make this statement little more clear, I can rewrite this particular statement of a theorem in an understandable way. The subset S is a subspace of a vector space V if S is closed under linear combination of any number of vectors. This particular linear combination of vectors will take care of closedness under vector addition as well as closedness under scalar multiplication. That is why the subset which is closed under linear combination of any number of vectors in S is a subspace of a vector space. Hope you are comfortable in understanding this statement of the theorem. I will give you another video which covers the proof for this particular theorem. In this example, two vectors u and v are chosen in R3, three-dimensional real vector space. Can W vector 9, 2, 7 can be expressed as a linear combination of u vector and v vector in R3. In order to check whether W vector can be expressed as a linear combination of u vector and v vector in R3, we have to check whether the scalars k1, k2 exist such that W vector equal to k1 u vector plus k2 v vector. That means 9i plus 2j plus 7k can be expressed as k1 times I plus 2j minus k plus k2 times 6i plus 4j plus 2k. Now we are going to rewrite this particular equation in a more compact form, which is system of non-homogeneous linear equations. How to do that? Simply we have to equate the components on both sides. For example, if we equate I component on both sides, we end up with a relation 9 equal to 1 times k1 plus 6 times k2. That becomes the first equation in the linear system. Similarly, if we equate the j component on both sides, we will get 2 equal to 2 times of k1 plus 4 times of k2. That becomes the second equation in the linear system. Similarly, equate the k component on both sides, we get 7 equal to minus 1 times k1 plus 2 times k2. Now this particular equation we have represented in the form of a system of linear non-homogeneous equation with two unknowns k1 and k2. Now the idea reduces to solving for the unknowns k1 and k2 by solving the linear system of equation. So we are trying to put this in a compact matrix form, which is nothing but the form Ax equal to b. Now the problem of checking whether W can be expressed as a linear combination of vectors in R3 reduces to the problem of checking whether the system Ax equal to b is consistent or not. Let us check how to find the unknowns k1, k2 by solving the system Ax equal to b. So B column matrix, column vector is nothing but the entry in the vector W bar 9, 2, 7. Similarly, the unknowns are nothing but k1 and k2. The component of the matrix A is nothing but arranging each vector u and v chosen in R3 as column vectors. So coefficient of k1 is 1, 2, minus 1, which is nothing but the vector u expressed in the column form. Similarly, what would be the second column of this matrix A? Yes, which is the coefficient of k2. Other way we can check the vector v represented in the column form. So arrange each vector as a column of the coefficient matrix and construct the system Ax equal to b. Then we have to solve for the solution. If Ax equal to b is having at least one solution, then the system is consistent, otherwise it is not. Let us quickly check the procedure of checking the consistency of the system. So we got Ax equal to b. We can visualize the solution space of the system either as a row picture or as a column picture, whichever is suitable and convenient for that particular problem. Sometimes by guess we are able to check what are the appropriate weights which when added will produce this particular vector very easily. At the time we can visualize the solution space using column picture. If it is tedious sometimes, then we can go by visualizing the solution space as row picture. For that we have to solve this system by using the well-known Gauss elimination method. For that, construct the augmented matrix by merging the coefficient matrix A with the column matrix B. Perform the row operation. First stage I have performed 2 times of R1 minus 1 times of R2 produces this. Then I have added the first row with the third row, produces this. Again one more row operation, add the second and third row of the reduced matrix. We end up with the final stage of the echelon form. Now we have to check whether the system is consistent or not. So, we are checking the rank of A matrix with rank of A augmented B. So, the rank of A is 2 and the rank of augmented matrix is also 2. Therefore, we can conclude the system is consistent. And how many solutions the system is having now? This rank of A and augmented should be compared with the number of unknowns. Here all these are matching. So, the system Ax equal to B is consistent with a single solution, or I can say as a unique solution. What is that solution? Use back substitution. We will end up with K2 as 2 and K1 as minus 3. So 2 times of K2, 2 times of 641 minus 3 times of 1, 2 minus 1 produces the expected vector 9, 2, 7 in R3. So, the system Ax equal to B is consistent indicates W bar can be expressed as a linear combination of U vector and V vector in R3. So, what is the answer to this problem? Yes, W vector is minus 3 times U vector plus 2 times V vector. So, the system is consistent indicates the vector can be expressed as linear combination of set of vectors in the vector space. Now, we will quickly recap the procedure to check whether the vector is a linear combination of given set of vectors in a vector space. So initially we will be given with a non-empty set of vectors in a vector space and an element in V. This element is not a member of this non-empty set, but we are checking whether this element can be expressed as a linear combination of the elements in the non-empty set of vectors. So to check W bar can be expressed as a linear combination of set of vectors in V, we have to check whether the scalar exists such that W vector equal to K1 V1 vector plus K2 V2 vector plus etc. plus K or VR vector. That is to check whether the system Ax equal to B is consistent or not. So how we are concluding about the linear combination by checking the consistency? Yes, if the system is consistent, it indicates W vector can be expressed as a linear combination of given set of vectors in V. On the other hand, if the system is inconsistent, then W vector cannot be expressed as a linear combination of given set of vectors in V. Hope you are comfortable in understanding the definition of linear combination of vectors in a vector space and also procedure to check whether the given vector can be expressed as a linear combination of other set of vectors in the vector space. Thank you.